Okay, so first we have to wrap up the lab for today. It's a lot of things, otherwise it's going to be challenging. So I have to look at the ports first. Let's do this. Let's save it as the lab 4, right? Remember we had, I'm not going to type up everything since we already have all the modules. So we have a couple modules. Let's just think about the ports. Okay, think about the ports. So what are the modules do we need for the adder and subtractor? First, you need the adder, right? So what are the ports for the adder? You need clock, A, right? The inputs, the carry in, C-1, and you need the overflow indicator, and also you need the data, right? Data is data output. And these are clock, A's and B's are 3 inputs. And this is just a wire, right? Just a wire. And then OV has to be used as a on the left hand side of the procedural assignment. So this is a rag. And we have a data, which is how many bits for data? The adder output. Adder output goes to where? Display, right? And you have a lookup table in the display module. So it is only 4 bits since we have no more than 16 entries. So we do this, and that's it. Okay? So that's for the module, for the adder. What are the ports for the display? So takes in the data, right? It's clock, definitely. But takes in the data from the adder. You can imagine another block next to the adder. It takes in data from the adder. And interface with the top, right? So it's a sag, AN and DP. So DPs are pretty simple. Just the one wire. And data is input, definitely, because data is from the output of the adder. So it's same width as for data. And 7-segment display, that's the output, because you have a lookup table in there, so it's the output. It's a rag type because on the left hand side of the assignment, and this has to be 7. Right, because 7-segment display, and AN has to be. I just put a 2 bits since we're only using the last 2 bits over there. and we assign an initial value to it. It's 1 bit. So we activate the sun bit first, right? So these are all the ports for the display module. All right. So it will be good for just display some static things. This is all the two modules, the two pieces of code were already provided in last week. So we were talking about adding a serial in, parallel out. So for serial in, parallel out, on the top, it's not a button, but we just call it button. Right. It's output, that's the debounce. And you have a button in. I think it's just called button, right? Just button. It could be a push button, could be a switch. Doesn't matter, because whenever you switch it on, there's just a rising edge. So this is a noisy one, and that's a clear one. So what's going to happen is whenever you switch this on, it bounces back and forth, and eventually becomes clear because of the mechanical vibration of the switch. And the clear one, the goal of this debounce module is to remove the noises and make a clear, very clear rising edge. The thing is, the digital system is running really fast, right? It's looking at the rising edge, or it could be a rising edge, could be a negative edge, right? So it's looking at the edge, and this has too many edges. It's going to trigger so many activities in the module. That's why I have to keep it clear. So eventually, just one edge. It's always at the edge, then you'll do something, right? So that's a debounce module. And this is definitely being controlled by a clock. So always, as the clock comes in, and whenever this rising edge, the noisy rising edge comes in, you clear it out, right? And this one is being used for the serial in, parallel out. And remember how many we have over here? Just 3, right? It's 3 bits. 3 bits. And this is used as a clock input for all these serial in, parallel out flip-flops. All right, and this is controlled by another switch, right? Switch. Could be switch, let's say 14. If we use this one, this is a clock switch, right? And let's say switch 15. All right, so that's the data. So you have 2 switches, right? 2 switches. One's here, one's here. 2 switches. You give a data switch, you give it 1, you have a 1 here, and then you give a rising edge and pull it back, just push and pull it back. So give a rising edge to the switch, so switch 15. So this one will create a clear rising edge for the serial in, parallel out. And these data is being fed into the adder. So think about the adder's structure. I have A, and these inputs are A's or B's. Should be A's, right? Should be A's. It could do both, but we just create one serial in, parallel out. Let's just call it simple. We just have one structure of this one, so we just use it for A's. Okay, so B's are already controlled by switches, directly feeding into the flatters, and these ones are A's. Do we need anything else in the middle? Do we need anything else in the middle here? So this guy, the simple, is just a structure, right? It's a box. Okay, imagine this is a box. Okay, the box has all the ports, and the ports is being interfaced with the adder. So the adder, we already have A's. See, it's able to take in the 3-bit data without any problems. So it's gonna be fine. All right, it's gonna be okay. And remember, these ones are that's a CM1. I got a 0, 1, a switch, C0, C1, C2. And C2 and C1, you got a little logic here, right? To get overflow indicator. And there's another logic, I think, engaged. Let me see if I have notes on that. But you guys should have notes for that, right? So that's logic expression for it's. So we used OV, C2, and S2. OV, C2, and S2. There's a little combinational logic to output C2 final. So your final output for the result. So this and this, and this. That's a 4-digit final result, and we call it data. That's 320, right? So this is being sent to the display module, right? And display module has a lookup table taking this data and then output a certain output pattern through the 7-segment display outputs. All right, and you'll need a top module to make the interconnections happen. A lot of times you need the wires in the middle. Let me give you some examples over here. So when we want to instantiate the SIPL and the adder in the top, what should we do here? This guy.
Send the outputs of the SIPO block to wires, and then send those wires to the...
Yeah, use some intermediate wires, right? Let's see if we can get some examples over here. So now we have adder. These are the ports of the adder. That's the display module over here. And then if we do a module top, let's call it test bench instead. So this one interfaces with the IPGA, right? So in that case, we need clock, SAG, AN, DP for sure, switch, right? Input clock, no problem. Input switches. Let's just declare all of them, just in case you need more over there. Switch. And definitely 7-segment display is going to be output. And AN will be output. We only use the 2 bits of AN. I think it's going to be fine. Let's just do it. DP is just 1 bit. Easy peasy. So let's instantiate the adder first. Okay, instantiate adder first. So it's gonna be it's called adder, right? Adder, and then the name of it could be adder as well. Just have one adder over here, right? definitely clock connect to clock without any problems. Let's see. What else? So the A's are the ports. Remember, what are the AAs? We also had AAs, right? So AAs are here actually. So they are not ports. We don't have to worry about that. But definitely the A's are the ports. So that's adders port, A ports. Adders A ports are shorted to. It has to be a wire, right? Because the display module also has output. No, the SIPL also has output. Let's just code up the SIPLs as well. SIPLs ports, what are they? Clock. The button, the switch, which is the button input. No, sorry, button clear, right? Because that's a clock, that's a cleared clock over here. And you need a how do we name the data here? We call it ICE. Button clear, ICE and PO, right? So if you look at this guy, this is ICE, this is PO. These are the ports. And input is button clear, input ICE, output PO. That's gonna be 3 bits. Okay, so that's the box of the SIPL. So PO is now available. PO is available, and PO will be what? Will be A's, right? You agree with that? See over here, parallel out 3 bits should be connected to A's. So how would you make the connection in the top? All right, so we'll need wire. Let's say it has to be 3 bits, right? It's called PO to A, maybe. So that's the top module. We create a little floating wiring here, and we instantiate the adder, and we connect the adder's A's to this wire. So this will be A to PO to A, right? What about B's? To switches, yes. So A's are serial in, so B's are parallel in, and parallel in data is directly from the switch. So you could use 3 switches here if you want. Oh, parentheses. Any other ports we need? Look at the adder. Look at adder structure. CM1, right? CM1 has to be a, because you turn on CM1, you activate the subtractor mode, right? So CM1 has to be a switch. Whatever switch you want to use. Let's do switch 3 probably. What else? So definitely all the ports need to be connected, and you have. So look at the adder.
The lab on this?
OV and data, right?
The lab on this says we should need to use this serial in parallel out method for A and B. So I'm just wondering if that's.
So it's more so it's more complex.
Okay.
Let's see. Oh, I forgot.
On step 3.
What about step 2? The switches as a certain input the short best one.
Yeah, that one doesn't use SIPO.
And
So I was just wondering if you're still
into 2.
expecting us to do that.
I think I just did a 1. See?
Okay.
All the B's are here.
Yeah.
Yeah, I think I mistyped the script over here.
Okay.
Input 2 3-bit numbers and B. I don't think the B word was a serial at all. Double check. Alright, this is a quick demo to the 3-bit subtractor and adder. So eventually, okay, 1 is nothing 0. Got changed. Right? So B's are parallel, A's are serial. Okay. Let's look at the adder. OV. So the intention here is to display OV on one of the LEDs. So in that case, for top, we need to add LED here as well, right? So go to here. Let's add LED. In that case, LED is the output. And even though we only used one, it doesn't hurt to declare everything, just in case you'll use it later. Oh, actually we do need it because the 4-bit outputs are being connected to the LEDs. So I have to display the 4-bit outputs. Looks like adder here. So the final output to the LED, the two's complement binary number to the LEDs, right? That's the first task. So these ones are actually shorted to the LEDs as well. Those 4 bits over here. But also it's being shorted to the data input of the display module, so you can send it to one of the entries of the lookup table to display a 7-segment display pattern. But the LED one is pretty simple though, so we can look into that later. Right? So for the adder, now we are at CM1 input. Let's connect the adder. No, the LED. All right. How would you approach that? Would that be just because the adder has, let's see, what's the adder's output? That should be connected to the LED. Data, right? Data is so data should be connected. You can directly connect the data to LED without any problem. So let's do it here. Data, we can connect to the lower 4 bits of the LED, so it shows the binary number over there. What else? So data. OV could be another LED. So OV is the indicator we want to display at the 5th LED. So whenever there's overflow, we can see it. It's just for verification. It's not a part of the calculator at all. So this could be LED for one, two, three, total is 6 ports, right? How many ports we have? 6 ports. Done. So we can. This is not needed. Do a parenthesis over here. Okay, that's how we instantiate the adder. Did you get the idea here? We do a intermediate wire to make the connections between the 2 modules. So if you declare 2 modules within the top and you want to make the interconnections, you just have to make a wire over here, right? So they can interconnect it. Let's do simple. Let's do simple. So simple has PO, right? So PO has to be shorted. So let's do clock first, always. There's no changes to that. And PO is should be shorted to what?
Did you put a clock on Sicko?
I should have done that. It's a button clear actually. So it has to be button clock. Thanks. Button clear, sorry, button clear. Right. Wait, button clear should be shorted to what's over there? Copy. No, button clear should be shorted to. It has to be another wire, right? Definitely shouldn't be the 100 megahertz one. So that comes from the debounce module. Okay, we'll work on the debounce module in a bit. So that's another wire because debounce will be another module, and this is the SIPL. They are interconnected onto one net, right? So that has to be a wire in your top. Let's just call it button clear, so don't change the name. So what's gonna happen is you just create a piece of wire here, right? Piece of wire here. Okay. So it's another no-brainer. You don't have to think about it. So in here, it's button clear connect to button clear. Okay, connect the wire. What about PO? PO should be P2A, right? Remember, here's a P2A wire. This is PO should be shorted to PO2A as well. Serial in should be a switch. And that switch could be, we were talking about 14.
Close in parentheses.
Yeah. something we missed over here. Look at the supples. Only 3 ports, so this is done. What about the display module? Display module here. Clock. Sag. AN. No problem. DP. What about data? So look at here.
Aren't we displaying data with LEDs though?
Yeah. So data should be shorted to LEDs, right? Yeah. It's gonna be 320. Is data also being shorted to somewhere else?
C2? No. That's X2.
No, it's going to where? Wait. So adders data is right shorted to the LED, so we don't really need. This is input, so this is not needed. The adder outputs data, and the data is shorted to the LEDs already, so we don't really need to do that. The data is also being sent to. So this is a tricky part. Let's see. So you have a adder outputs the data here, 4 lines, and you have a display module takes that in and output a 7-segment display, a SAG pattern. It's from 6 to 0, right? And at the same time, your top is also taking in that 4 bits data to the LEDs. How do we deal with that? So how do we deal with this guy, the data part? So the same data line is being shorted to so many different places, right? So in your top, if we create a wire here, we could code it in a different way, but also we can code wire data. So it's going to be a wire 320 data in the top, and then we can directly assign this to this guy outside of the always block. So no matter what data is being created, it will be directly sent to the LEDs. And also it's a wire, so you can have this one connect to this guy and this one also connect to this guy. So they are indirectly shorted to each other. So eventually these two are interconnected. Alright? Any questions on this? It's a piece of floating wire in the middle. So in that case, for our code, let's take a look. Let's take a look at it. So we need to change. First, we need to add a wire, 4-bit wire in your test bench and call it data. Or data wire, just trying to differentiate it from that. There's a data wire in the top. So this creates a little piece of 4 bits of wire over here. So since this is available, we could we don't do this, right? We don't do this. We don't directly connect to LEDs. So data shorted to data wire. Okay, so data shorted to data wire. And then your display module. Display module. It's going to be the input port, which is data, shorted to data wire as well. Okay, and I think that these are all the ports for display, right? 5 ports. 1, 2, 3, 4, 5. Yes, 5. That's everything. And so we can close it. Close it. So in your top, you could just have a sign, right? Just directly assign for here. You're gonna add it to the top. Assign what? Assign LED. No, assign data wire to LED. I think this will work. Let me see what I did over here. Yeah, you can do that. You can either put on the top or bottom, doesn't really matter. Okay. So this is a major structure of the connections of the digital blocks, right? So all the boxes, how we make the connections, especially on the top, from the top module. So the major idea is that if you have several sub-modules that are interconnected, you need to create a wire in the top to make the connections. For the adder, also for the A's, okay, for A's, and also for the button clear output. So that's for the debounce module, okay? So now let's work on the debounce module. Any questions for the top over here? Any questions by far? All right. Let's move on to the debounce. So remember, the debounce has a clock, right? Clock drives it. So whenever there are some changes, the clock will synchronize the changes to the output. So we need a clock, right? Okay, this guy, the clock to update everything, and we need the switch in and switch out. So it's really simple. It's just one clock controls and synchronize everything, and then you have a dirty clock and you have a clean clock. Okay, and the clock is just basically a switch. So this is what we need, right? We need this. We just design it that way. Module. So definitely clock is the input. Button is also input, even though it's shorted to the switch. And we need a button clear as the output. And because we can imagine it's going to be always block on the left-hand side of the equation of the procedural assignment, so we just make it rag. Otherwise, Vivado is going to report errors to you guys. Always at positive edge of the clock. Positive edge of the clock. So the idea is that you create a little time delay, and as long as let me see. If the output and the intermediate variables are not the same, then just make them the same. So the way to do that is you create a little time delay over here. It's called parameter delay. I tried several different parameters. I think this one works, but it doesn't have to be this one. I'm using a 6.5 milliseconds. Let's do 6.5. 1, 2, 3, 4. And we need a counter. And the counter, I mean, using an integer counter is pretty big. This is from the textbook, right? This is from the textbook. I don't believe we need a 32 bits because integer is a 32-bit variable. And starting with a 0 as a counter. And we create an intermediate register type. Let's call it lec9 equals 0. Right? And then if I'll just type it up. Button, the input is not lec9, then we clear the counter. And also give the button's value to lec9, right? So because the clock's running really fast, so every time they're not equal, and the clock will synchronize it. So eventually the button's value will be the same as the lec9's value, right? It's going to be the same. It's going to keep the same. And then else if, so whenever the counter equals the delay, the count equals the delays counts, we assign the output, we assign lec9's value to the output. Else just count, right? Just count. What's a good way to understand this code though? How do we understand it? So lec9 is eventually sent to the output. So before the time delay, there will be bounces back and forth. It's going to bounce back and forth, right? Bounce back and forth. If it's not reaching the time delay, it's always trying to synchronize the input to the output. Whenever it reaches the time delay, it just give the intermediate value to the to the clear output. So it's like a low pass filter, right? So the high frequency bounces won't be sent to the output. Only happens whenever it reaches the time delay, which reaches the number of count we set up over here. This could be I mean, there are many different ways to do debounce. This is from the textbook and it works. I think we can use it, even though it's probably not the best way to do it, but which is fun. I think this is fine. Let's just keep using this guy.
Should we do count greater than equal to delay? What is that?
Yeah, I think this is over a better. Usually, it's a better practice, right? I agree with you. This counter. All right. So this is the last module we're going to cover for this other subtractor lab, and I think by far we have all the modules already covered. Yeah, I think you guys should be fine for that, including the top as well. Any questions on this for the lab this afternoon? It's a little bit challenging because all my typing here could be some typos, could be some bugs here and there. So it's a debugging process for you guys to do the labs. But you get the concept, right? So the structure is already given. You guys just put all the modules together, right? Yeah, and this is also recorded. I'm gonna post it after this lecture. So you can use this as a template, right? And then start inserting your modules into this template. And you can keep all the sub modules into one .v file, right? Including the top. So the only disadvantage is that this will make it very long, right? You could use a separate .v files, and you can split the window into separate ones horizontally, so you can open them up at the same time in Vim. We'll code it up, right? But after you are done, you load it to Vivado, and you can debug over there after that. But this really helps for typing and working on different modules at the same time. Okay, alright, I spent so much time on this module, on this lab. I'll move forward to the next one. I'll give you guys a 3-minute break, right? It could be too long. So you can also work on the in-class, the last problem there as well. Okay, now let's go to the next one, which is you guys will be a little bit busier this week. All right, we have a tutorial covers the data storage units, especially one of the clocks being used. It's the IP from Vivado. So you guys learn how to use IPs for ASIC design. So it's basically a module provided by Vivado. You can directly declare it from the IP. So this one is due Tuesday next week. So you guys have a week to work on it. And so Thursday, we'll introduce UR, and that one is due the week after. Okay, you got 2 tutorials due in 2 weeks, and including labs, right? So this week's lab is the tools complement, and next week's lab will be the LCD display. So 2 labs and 2 tutorials. It's a lot of work. The next lab is due here. Yeah, it's about 2 weeks, a little bit more than 2 weeks. When you have two labs and 2 tutorials, all right? Be a little bit busy this coming 2 weeks, just to let you guys know. And I will try to not adding another quiz. This is 1 quiz, and then that's it for 2 weeks. Okay, no more quizzes. So this one is pretty simple, I think. That's why it makes sense to have 2 tutorials in 2 weeks. So this covers the ways to model latches, and it's all behavioral modeling. So you can see you just describe it whatever you want a circuit to behave. So it's actually pretty simple compared to digital logic design. You have to think about the circuits and everything else. So that's a fundamental SR latch. And I think it's still good to remind you guys on the things over here. Let's see. SR latch. There are 2 different structures. You can use NAND gates to form SR latches, or you can use NOR gates. So my question for you guys is, for some of you already took VLSI, so which is S, which is R? When we define this is Q, this is Q naught. Let's see it. So SR means set and reset. So when you set it, Q becomes 1. When you reset it, Q becomes 0. And we are always talking about Q, right? Or we're always talking about Q. So assume that this is S, this is R, and we'll see if this is right. So if we give a 1, and the other one has to be a 0, because that's the fundamental rules of the inputs of the SR latch. It cannot be the for NAND gate version. Could you give 2 zeros at the same time? No. Nope. So for zeros, it's invalid, right? It's invalid. But so it has to be 1001 or 11. So 11 is gonna be a memory. All right. So for 10, if we do a zero here, and this will be the output will be 1. So 1 comes here, right? And this becomes 0. So this is not right. So it has to be RS, right? It has to be RS. So now we are trying to reset Q, which means we need a 0 to Q. Okay, so we turn on R and turn off S. So it's 10 RS, 10 RS. Okay, and this one gave a 1 and eventually got a 0 here. So Q is reset. So whenever you turn on R, you are resetting it. Good, right? For the NOR gate version, let's assume this is S is R. It might be wrong. So 1 0. So for NOR gate, we're looking at 1s or 0s first. Should be 1s, right? Because 0 will not give you a definitive answer over here. So I have to do 1s. So 1 OR gate, NOR gate will be a 0 here. It's gonna be a 0. 0 comes back. 0 0. It's gonna be a 1. And this is not right again because you give a 1 to set, you are trying to turn on the setting, but this Q is being reset. So 0 here. So that's this pin must be a reset. So for both structures, it's going to be RS. So R on the top, S at the bottom. For both, right? So Q, assuming that Q is on the top. So you are setting and resetting Q, not Q naught. But this is symmetrical, it's equivalent. If you name the bottom one as Q, the top one as Q naught, which is still fine, right? You just flip it, right? Just flip it. But now since we define the top one as Q, so we are always setting or resetting Q. Okay? So that's the latch. And we could create all different circuits using the latches. But for here, when you model it with the Verilog, it just everything becomes simple. So you just look at the truth table and describe it. So see here, SR latch, SRQQN, It's from the textbook. Okay, from textbook. You can see behavioral modeling always SOR depending on which changes. It's a sensitivity list. Because the latch doesn't have a clock, right? So whenever SOR changes, it updates the output. So it's even giving a 10 or 01 to the output to Q and Q naught. Is that interesting? So you see, whenever these changes, this changes, if S is 1, it assigns 10 to the output. If R is 1, it assigns 01 to the output. So it doesn't take care of the invalid inputs, right? And you can see when S is 1, it follows. So 10 here is a combination of 10 follow the order. It's actually QQ naught, right? Because it's 10 QQ naught 10, right? So whenever S is on, it turns on Q because it's the 1 here. So when S is 1, Q is 1. When R is 1, Q is 0. It just does whatever the SR latch does, right? But doesn't include the memory mode, does it? Is there a memory mode? No. So it's basically just the latch, without the memory mode. It's not being used. It's not being used. Okay. And here's the latch. So this is from the textbook, right? And I put in the Vim, and then I created a little test bench to verify it or to simulate it. So this is the result, right? And I can form a SR flip-flop. So SR flip-flop like this, and there's truth table, and you have the models and also the top module as well, the test bench, right? So initial begin. So for this test bench, only runs everything once. So it includes a clock, but the clock is always 1. See, it's the SR clock, and did a concatenation here. It's 1, 0, 0, 0, whatever, all these states, and clock is always 1. So it's always on. It's always on. The reason for that is you can see clock is always in the condition. So whenever clock is not on, this won't be satisfied. So none of these will be done, right? So that's why I have to keep the clock always on here in the simulation in order to see any results. All right, so these are these latches. So similar ones over here until a point that you see a memory file, okay? It's a ROM. So we have to cover ROM because ROM is being used for the softcore tutorial at a later time. So it's pretty exciting because exciting to see how it works, right? So you put your assembly. So there's I think it's assembler. So assembly code into a memory file, and then you compile it. And it will be able to convert your assembly code into a ROM file. And it's a .v file. It's a ROM.v file. It's going to be a memory file in Verilog and contains all the machine code of the assembly code, and also some Verilog structures in there to put all the assembly in. So it's not this tutorial, but the tutorial later. So that's how you put your software, the code, into your hardware. So it's important to learn how to use ROMs because these are memory files. So you can see here the first ROM file we modeled. It has address, has a read enable, chip enable, and memory. So the memory we we name it as a memory.mem, MEM. You open a text editor and you copy and paste, or you can, I don't know how these were created. I think I just typed in there. If you want to use the Python, you can use Python to create all the binary numbers, which is fine. But I think these are just some random binary numbers. And you'll save them in the text editor, right? And you have to change the extension to .mem. Okay, you have to change it to .mem in order to read it into your Verilog. You see how it's being read over here? $ read memory. B means it's a binary file. So whenever it reads it, so that's something is available in Verilog, right? In Verilog. So whenever it's a binary file, you have to put a B here. So it recognizes the numbers as the binary digits instead of a decimal or other formats or number systems. So it reads everything into this variable called MEM. And this is another register over here, see? So what this does is the memory file is something you typed into the text editor, and when this is being read, they store them into a register data type in your hardware. You can just imagine these are probably just the different flops, just latches. They are being latched. So the data file in the ROM you typed into as a text in the text editor will be latched into a register type memory by this line of code, right? So it's reading it from this file you just typed into this register type in the hardware. Okay, so after that, you will be able to read everything out from this guy because it's being saved in there and has multiple lines, and every line has an address with it. Everyone has an address with it. So take a look at this example over here. That's the test bench for the ROM. Okay, and this is the top is the ROM's Verilog module. Let's see how that works. So we have these ones as the ports, input address, output data. The 8 bits will be output to the data variable, and you have read enable, chip enable, and that's the memory variable, the register type memory, to hold all the data from the ROM. Okay. So what does this mean here? You can see so when I declare this register type, I have 7 to 0, and also I have 0 to 255. What does that mean? What is that? Why the first one is from a larger number to 0, and the second one is from 0 to a larger number? So the first one is the width, right? It's 8 bits, and the second one is the index, actually. So you have 256 lines of 8 bits. So it's actually 200 from the address is going to be from 0 to 255. So every data is 8 bits, right? So that's the width of it, and it's going to be a memory bank from top to bottom. So totally there are 256 entries of 8 bits numbers in there. That's how you declare that variable. Okay, that's the way to declare that. And then, so the ROM is a memory. So the memory has data, but also has some peripherals like digital controls. That's what the other Verilog description, the code, what they do over here. So you can see, for example, this is the first logic. So CE, chip enable, it's called CE. It's just a little control port, right? So CE has to be 1, and read enable has to be 1 as well. Okay. Is it 1 or not, right? So this is the mux. This is the mux. Remember the mux structure? Something, the condition, and question mark. And if it's a 1, it's going to pick up the first one. If it's a 0, it's going to pick up the second one. And they are separated by a colon here. Colon symbol here. So if it's being enabled, then I take out that memory at the memory entry or the data at this address. So the address is the index, or you can call it just address. Okay. So it's gonna, what's that?
What does the question mark do?
It's a mux. Remember the mux we did at the beginning of the semester?
Okay.
Yeah, this is a 2-to-1 mux, right? 2-to-1 mux. So if this is 1, pick up the first one and send it to data. And if 0, which means it's not enabled, you just output 0 to the data, right? So it should be nothing to data. So these ones are the ports of the ROM, and they are controlled by the top. So we don't have to worry about this for now. So the top will be able to handle that, but the top has to be has to send the enable signal to it, right? Both chip enable and read enable in order to activate it. So it's gonna read whatever here. So the address is also the input, right? And the memory block itself doesn't have to choose the address, because the address is actually a request from the external module, right? The memory has address, has data, right? So the data at certain addresses, but the memory is just a memory, right? You have to, whoever is using the memory is going to tell the memory which address, which data at which address I want to take out from the memory. So it doesn't really have to care about that. It's just directly put address as an index in here, right? So no matter what address is being requested, it just directly put in here and take the data out at that address and make it available at the data output. Does that make sense? And that's it. It's pretty simple. That's it. And the memory is available because you have a read memory binary, this command, and just it's being just executed once because it's being placed in initial begin, right? So it's only executed once, it's putting here, and then everything will be loaded into MEM, so the MEM becomes available over here, so you can use it. Okay, so for the top, so these are the enables. It's an internal register, so you can tell that you just give a 1, it's being enabled. And these are the addresses, also the internal register type. You can imagine this will be just a simulation, right? Simulation. So you can see the simulation over here. So the $sign monitor shows the format of how to display the simulation over here. Okay, so these are certain arguments. So for example, address, I want to show a hex format, data I want to show hex format, and read enable and chip enable are both binary formats. Okay, and so see here, I just make a time delay, right? So time delay and a for loop. So this is being put in the initial begin, so even though it's the loop, but the loop will be only be executed once. After it's done with all the 256 loops, it will be done. It won't come back again. So this is initial, it's being put initial begin statement, only executed once. And it's just giving, you see, it's actually a very simple structure. It's enable 1, enable 0. So it enables it and disable it. So you can see whenever it's getting enabled, you got a data at the output, and whenever it's being disabled, you got a nothing. So it's just showing you that data 0, data 0, data 0, data 0, and the 0 output is from the mux over here. So either enabled or not enabled. Enabled, not enabled. So you can verify your functionality of the mux over here, right? So that's a loop to display the data, and also make the connections whenever a certain address is being sent to the address port. The data at the address will be sent out to data, so you can display it at the monitor. Okay, and that's it. And there's even no clocks, right? Because you don't need the clock. You don't need the clock. In simulation, you are just creating a time delay to send the different addresses, to the memory, and the address is being shorted to the address of the memory file, and it will output the data over here. See? Okay, that's how to use memory files, ROMs, and read the memories and display it from this example. I will talk more about it on Thursday. There are a couple of other examples to be explained. But other than that, we are fine. So see you guys in the lab today to work on the adder subtractor stuff. Okay.